Welcome to this A-level lesson on electric potential. Now you may remember from a previous lesson that we've looked at gravitational potential. So let's think about the definition of gravitational potential before we move through this. Now gravitational potential is the work done per unit mass in moving a mass from infinity to a point within a gravitational field. Now, because gravity is always attractive and these are pulling towards each other, the work done is going to be negative in this particular case, because you're not having to push the masses towards one another, you're allowing them to fall. Now, similarly, we have electric potential with a very similar definition. However, with electrostatic fields, we have positive and negative. So there is one definition for electric potential, but it is based on the positive test charge. Now that is to say that the electric potential is the work done per unit charge in moving a positive test charge from infinity to a point within an electrostatic field. Now, that means that because positive charges repel one another, if it is a positive charge producing the field in the first place, work is done in moving the positive test charge towards it. So that means electric potential is positive around a positive charge. Conversely, since positive and negative attract one another, if we have a negative charge creating the field and we have a positive test charge, then this time the work done will be negative. And so we say that the potential around a negative charge is going to be negative. So let's have a look at a couple possible examples. We may have, for instance, a positive test charge here. Now, if you have a positive test charge, we might have an electric potential. So we can actually draw around this an area that we call an equipotential. Now, an equipotential is a surface, equipotential. I'm going to move those out of the way. So, an equipotential is the surface around a charged object of constant potential. So the potential is the same everywhere around this. So for instance, it might be, since we're talking about the work done per unit charge, that means it's going to be joules per coulomb. So we can say that V, our electric potential around this surface, is going to be equal to, let's say it's 300 joules per coulomb. Now that means the further we get out, if we are further away, the energy required to reach a point further away from all the way over here in infinity, the energy required to do that is going to be less. And so the electric potential at this stage might be, say, 250 joules per coulomb. So we can see that around a positive charge, the equipotential surfaces become increasingly positive as we get closer to the positive charge. Just as within gravitational fields, you've seen that the equipotential surface gets more negative as you get closer. And then similarly, we can look at the negative charge, and we can say that we might have an equipotential surface, a surface of equal potential everywhere, where V is going to be, well, let's say minus 300 this time. Okay, joules per coulomb. And then one slightly further out, and we can say that moving an object from infinity to get to this point could be 250 joules per coulomb. Now generally when we draw these surfaces, we make it the same, what we call potential difference delta V. We make it the same potential difference, but what you will find is that as these surfaces get further out, because the electric field strength gets so much weaker, the actual distance delta R changes. It gets bigger. The further you are away from an object, the bigger this radius will become. In fact, the bigger the difference in radius between each equipotential. So in here we'd have one that's extremely close. So you see the distance is small here, the distance is getting bigger, delta R is getting bigger, and delta R is getting even bigger. And this one here would be, let's say, well, if that's minus 300, it's minus 350. Because delta V should remain the same. Okay, now next what we're going to look at is what happens when we have two charges near one another. Now we'll start with two positive charges. Now their equipotential fields interact with each other. What we have this time is we have a positive charge here and a positive charge here. We can say that there's an equipotential surface here, equipotential surface there, but their electric fields are interacting with each other. So because these are repelling one another, we've got our electric field lines going out this way. But we've also got this. The electric field lines will not meet one another. Now, when we draw our electric potentials, or at least our potential surfaces, so our equipotentials, we always draw them at right angles to the field lines. And when we're drawing them at right angles to the field lines, we end up with some interesting shapes. So if we draw this, this won't be perfect obviously, we can see that we have an equipotential surface that covers both of these. So we have an equipotential here of, let's say again, it is 300 joules per coulomb. And this one is also going to be 300 joules per coulomb. You can see that this connected equipotential everywhere along this surface is going to be 250 joules per coulomb. So everywhere along this equipotential surface is going to be the same potential. That's why we call it an equipotential. Okay, let's have a quick look then at a negative and a positive. What we would find here, we'll do positive there, negative here. This time what we find is the electrostatic field lines, they connect to one another. Okay, remembering that we're always pointing from positive to negative. In fact, you might even recognize the field as we add more lines to it. You might recognize that this field is actually very, very similar to that of a bar magnet, because we've essentially got two poles here. We call it a dipole, and we also have the same situation with a bar magnet. We have a dipole, because in the case of a bar magnet, there are always two poles. Now, since we've got this situation, our first equipotential surface is relatively undisturbed. Okay, so we've got this one is going to be plus 300, so that's 300 joules per coulomb, and this one is going to be minus 300 joules per coulomb. But you can see we've got a lot of change to happen here. What you find is that these surfaces bunch up. So you see here we've got, between these 2 points, the surfaces spread out quite a way away from the charge in either side, but close together here we have our equipotential lines bunched up as it moves from a potential of plus 300 joules per coulomb to minus 300 joules per coulomb.